Hello, my dear audience. Today I'm coming with a new course named as Theory of Structures. This course is very known in that it is dealing with the analysis of structures. As you know, analysis of structures is the very beginning in the very beginning phase of the design of structures. Generally, there are 4 steps that we know. During design, the first thing is modeling of structures. Then once we model our structures, we are going to load by different types of loads, and then followed by analysis of structures. We analyze structures. Then finally we design our structures. So in order to go across these 4 steps, we need to focus on this theory of structures. Okay, theory of structures has different chapters, in which I will try to start one today on. This is the first chapter, that is modeling of structures. Modeling of structures. Okay, here, before directly going to modeling of structures, let me try to define what a structure is. Structure. So we can define a structure as a single material or assembly of different materials that is connected each other in an appropriate pattern, such that that material is capable of transferring load. So a structure can be defined as a single or assembly of materials capable of load carrying and transferring. So these 2 words are very important. If the given material, whether it is single or assembly, if it is to be named as a structure, it should be capable of carrying a load. So the very importance of a given structure is to carry a load. Once again, it should be able to transfer the load to another load carrying system. So if that single material or assembly of material is having these 2 properties, that is capable of carrying load and capable of transferring load, we name that material as a structure. Okay, let us come to the modeling of structures. So what is modeling? Modeling of structures. So this name tells us modeling is representing a structure. We have different types of structures in the real world. We can name the most popular ones: buildings, we can name bridges, we can name transmission towers, we can name dams, we can name different types of structures. But almost all of the structures that we are encountered within our day-to-day life are 3-dimensional structures. But when we are dealing with the analysis and design of our structures, we may not go to the 3-dimensional representation of structures. So our structures, the real structures that are encountered, either that are taught in our mind, or those which are going to be constructed in the real world, should be represented by some reasonable representation. So this reasonable representation of structures is named as modeling. So simply we can name it as representation of structures. So different structures and structural components are going to be represented reasonably by some representing structural components. So this is named as modeling. Modeling is a very, very important procedure during the design of structures, because if we are lacking the correct or the best representation of our structures, if we are failing in representing our structures correctly or reasonably, then the other parts following the representation of the structure or the other procedure that follows the modeling of structure, like the loading, the analysis, and the design, will not become with the right answer, because we are just mismodeling our structure, or we are misrepresenting our structure. So all other procedures that are going to be applied or that are going to be handled on a mismodeled structure will bring nothing but results, because at the very beginning the modeling is becoming inappropriate. So modeling is very, very important. Let me try to give you some examples of modeling. For example, if you come to the buildings or some structures, there are beams. There are beams. As you know, beams are usually horizontally aligned structural elements in which their lengths are much, much greater than either their widths or their thicknesses. So actually, based on different design codes, the definition might be somewhat different, but usually a given construction material, component, or structure is going to be named as a beam if its length is greater than or equals 2.5 of, larger of, or max of either its width or its depth. So if a given horizontally aligned structure that is capable of load carrying and load transferring has, if the length of that material is greater than or equals 2 or 2.5, is different in different codes. Let us take this one, 2.5 of maximum of the width or the depth, that then we name it as a beam. So by definition, practically we are saying that a beam is having a length, it is having a width, it is having a depth. So it is a 3D structure, but in representing these structural elements, either in softwares or in representing it in the manual calculation, we represent it as a line structure. Line structure. So when we are drawing beams, usually we ignore their width and their depth. Their value is not ignored, but when we are drawing them, we are only drawing the width, the length of the beams. So the 3D beam is represented as a line element. So this is the representation or the modeling of the beams. Let us add another example. For example, let us consider columns. Columns are vertically aligned load transferring elements or structures. They are also having more length or height as compared to the cross-sectional size, so they are also represented as lines. They are represented as lines. Okay? When you come to slabs, slab is usually it is a flat or horizontally aligned structure, but this is having much less thickness as compared to its length and its width. So if this is the top view of a given slab, if this is its length L side, if this I mean Ly, if this is Lx, so one longer side, another shorter side, or equal maybe, the thickness is much less than. Its thickness is much less than either of these two values. So if the thickness of the slab, if the thickness of this horizontally aligned structural element, the slab, is much less than either of its sides, then we can represent this slab as a 2D element or a 2D structure. So slab, although it has length, width and thickness, but when we are representing the slab, it is represented as area or surface element or area structure. The same is true for walls. Walls are also having smaller thickness as compared to their length and width. So as compared to their length and width, their thickness is smaller, so they are represented as area objects or area elements. So we may have also different representations. These are some of the most important representations of structures or modeling structures. This is the representation of structural elements. But when we are saying modeling, it's not only dealing with the representation of structural elements. It extends to the representation of support types also. So support types are also represented. We have different types of supports practically, and once again it's quite difficult to exactly represent what is happening on the real world structure to represent the connection type or the support type, but some of them are straightforward. They can be represented well. So let me focus on some of the representations. For example, I may have pin connection. This is represented by such a representation. Okay, this is the point where a member is going to be attached. This is the support. This is pin support or pin support or pin connection. Okay, this pin support. So if I have a member, for example, let me draw like this. This is a beam because I am representing it as a line, so this is a beam. Or this might be one of those members. Okay, don't bother about that, but this is for the time being, this is a beam. So this connection is named as a pin. Why I am naming as a pin? A pin by definition allows rotation about a given axis, but allows no translation about along any direction. So this has, for example, if I am setting coordinate here, this is x direction and upward is y direction, then into the page will be z direction. So along the x-axis, this member cannot move because it is connected to this one. It is not allowing any movement along the x direction, either forward or backward. Once again, this member cannot displace upwards or downwards because it is connected here. So this connection is allowing no translation. So no translation along x and along y direction. But this member can rotate about this connection without translating to either of the coordinates, either x or y. So there is rotation about the given point. So if the connection type is resisting movement of the member along either x or y direction, but allowing the member to rotate about the connecting point, so the connection type or the support type is named as pin support. This is the representation of pin support. Whenever we are thinking of, or whenever it is feasible to represent the connection between or the support nature of a beam to another supporting element as a pin connection, so we can represent this pin connection, or we can use this pin connection. So this is one of the connection types that exists. So another connection type is the roller type of connection. So the only difference between roller and pin type of connection is that when it is roller connection, translation along one of the direction is allowed. So roller is represented like this as a ball. So if I have, this is the roller connection, if I have a member like this, so along this perpendicular to the contact surface, that is along this in the y, positive or negative y, translation is not allowed. But along the other direction, either forward or backward, movement is allowed. So here, no translation. But along the x, either positive or negative, translation is yes, okay? Translation is possible. And as you see here, the connection, the member can rotate about this point freely. So there is also rotation. Rotation is allowed. So if a beam member is connected to a given support, say that member can rotate about a point within the connection and can translate to either of the directions, either along the x-axis or along the y-axis, but not both. Then we name that support type as roller. So this is the modeling or representation of roller supports. Another support is fixed. Now fixed is different to the both types of supports that I stated before. It is represented like this. This is the representation of fixed support. If I have a beam member, for example, like this member is connected to the fixed support at this point. So a fixed support doesn't allow any translation. It doesn't allow any translation. Either upwards or downwards, this member cannot move. And either to the left or to the right, this member cannot move. Not only this, the member cannot also rotate about this point. So movement is also prohibited. So no translation. Both x and y. No translation along the x, no translation along the y. And no rotation. So such type of support is named as fixed support. Another support opposite to the fixed is free support. Free support. So the support is just not to be visible, but it is expressed in terms of the member. For example, this member, at this end, as you see, nothing is appearing here. Okay? So this member can move upwards, downwards, or left, right, can rotate about any point given here, about at this end point. So this member is free either to translate or to rotate. So this is named as free support. So there is just translation. Translation is free or allowed, both x and y. And rotation is also possible. Yes, rotation. Okay. My dear audience, I am not finishing all types of supporters, so I will return back in another video the rest types of supporters, and I will come up with a summary of the modeling of structures for today. I would like to say thank you, and I'm expecting your subscription to my channel, that is in the Mama with Johannes, your comment, and I'm expecting you to share my channel. Thank you very much.